Okay, so I would like to thank the organizers for inviting me to speak here. Okay, so I'll be speaking about a somewhat different topic, I think, than most speakers here will be speaking about alchemical transition. So I will discuss reaction coordinate sampling here. And we're working towards optimal sampling. It's questionable if one can actually achieve the optimum, but I'll show you how we're working towards that. So most of this work has been done by my PhD student, Jivka Lindahl. As all of you will probably know, molecular dynamics is a powerful tool, but it has problems with sampling rare events or transitions because the timescales you want to sample are often much longer than what you can achieve in molecular simulation. So here's one example. We were looking at the opening of a loop in an RNA system, and then if you would just run MD, you would only see one conformation, not the open one. So you would need to do something to actually see the other conformation, and for that you need to bias your simulation if you want to see that in a reasonable time. So you need to add some reaction coordinate to make this work. And then you need some method that actually allows you to drive the system over transition barriers. And that's one question is, what kind of method should we use? So I wanted to focus actually on a different topic here on optimization, but I think I need to discuss the method, especially after discussions we had yesterday. So the basic idea is that one can bias simulation. So if you do your normal simulation, you would get a Boltzmann distribution, which is this blue one, but I can add a bias to my simulation by changing the Hamiltonian in any way I like, and get a different distribution out. So find something that's, for instance, flatter, which would likely allow easier sampling between these minima. And then once I have this, since I usually know what bias you've applied, you can unbias and get what you want back. So that's the basics here, which is rather simple. The question is then, how does one do this in practice conveniently and correctly? So a very short presentation of methods to do this. So there's an enormous zoo of methods out there, but I think the field is slowly converging towards the same kind of thing, which is good, I think. So the most well-known method is umbrella sampling, which is very simple and powerful. But the issues there, as I'll also show here, is that it slows down sampling by restraining your system. So you add an umbrella along your reaction coordinate, and you sample different umbrella positions, but independently. So this leads to nice trivial parallelism, but since you fix your system along the reaction coordinate, it's not free to move back and forward anymore, and this will slow down transitions. The other issue there is that thing we've also been discussing yesterday, that it's difficult to move from the initially chosen pathway, so you need to set up initial structures to generate your starting states for the umbrellas. Once you've set that up, it's difficult to move these over barriers perpendicular to the pathway. So then there's a very popular class of methods, which is now referred to by metadynamics, but the ideas are much older. Local elevation or flooding by others in the field before it was picked up and popularized as metadynamics. So this has dynamic sampling along the reaction coordinates, which has strong advantages because you make use of the natural sampling of the system. But the disadvantage here of these methods is that there's no explicit target distribution. So you don't know what this distribution is that you're after. Maybe a posteriori you might know. So what I'll shortly describe now is the method we've been working on, which is called the accelerated wave histogram method, which is a very general method. There's nothing spectacularly new there, but this actually adds the thing that you have an explicit target distribution in there. So this is nice. So you have control. You can control what you want to get, but you can also check what you're getting, since if you're not sampling according to your target distribution, you have an issue. Okay, so the basic procedure is the same for all these kind of methods. I start out with some initial bias, which could be no bias at all, and then I run a bias simulation. I observe what I sample. Then from the samples, I estimate the real distribution, which is usually unknown. And then I can update the bias, so I can come up with a new bias based on that. And then with the new bias, run a bias simulation again, and then iterate until you're happy. So how do we do this with this AWH method? So this is the version we use is tailor-made for extended ensembles, where you add a reaction coordinate, which could be anything. It could be an alchemical parameter. That's not what we use it for. So we actually use it for reaction coordinates, which are generalized coordinates of the coordinates themselves, which adds complication. But and then the elements here is that we use an efficient update scheme to estimate the distribution and to update. And yeah, we explicitly include the target distribution as said. So I can't go into much details of the method here. I'll just quickly show how it works. So we initially had a scheme where we had molecular dynamics in your normal phase space, and then you have your your reaction coordinate here is given vertically along lambda, where we do Monte Carlo sampling on lambda. So you have your umbrellas and you jump with them. So that's shown in the next slide here. So you could do umbrella sampling with individual runs, but here we jump with Monte Carlo between the umbrellas based on your target distribution and what you observe. Now we actually have a preferred way. We convolve the umbrellas to get a convolved potential, and then you can just do MD. So that's very similar to what metadynamics does with dumping Gaussians. So we're pulling on the system, but not with a constant rate. And the system, in the end, if the updates will be small, you're not pushing the system anymore. You go to equilibrium. Okay, so one important ingredient here is that we have an exponential linear weight decrease, which automatically tunes the time of the system. So you need to have some parameters in this method, not many. But one is by how much should I update? Like if you do metadynamics also, what should my update size be? So our trick here is that we initially had in the initial phase, I had updated slides, but I got the wrong ones into Berk. Okay, so initially we have a constant update size, and then once we cover the whole range of the reaction coordinate, then we halve the update size. So that gives exponential decrease in update size. One can do this when the errors is large. When the errors are larger than KT, one can be in this exponential kind of phase. But at some point, when we cross the diagonal here, where each sample has weight of 1, then we switch to a linear increase, as you would expect. So in the end, samples should count. The variance should go as 1 over the number of samples. You can't beat that. So the Wayne-Landau scheme will go wrong at some point. But since we keep track of this crossing point, we automatically tune the update size for the timescales in the system here. So this gives us very, very quick convergence to errors of roughly KT, and then we get the normal, unavoidable convergence with the variance going as 1 over the number of samples, or 1 over time. Okay, so just to show you that this works, so this is a toy system. So there's basically only one critical parameter, so we can choose the umbrellas as tight as we want. That doesn't matter for the computational cost. So there's one parameter, which is the initial update size. So how much should I initially change my weights or my bias? So here I've shown this is the inverse size of the update, or it's the weight, and shown for many different, large range of values. And you see that they all converge roughly equally quickly to this regime of one variance goes 1 over m, except if my update size is very small. So if it's very small, then I just need a long time to fill up minima. So as long as you take it big, it's fine. You can take it very big and it works. So this is non-critical. Okay, so then actually show that this works on a realistic system. It's another, sorry, with this sending slides to Berk, a lot of stuff disappeared. Okay, so this is an example application here. So here we're looking at base pair flipping. So the reaction coordinate here is this Watson-Crick hydrogen bond, and we want to see if bases flip out. So we just have one reaction coordinate, but there are 4 different moves can happen depending on which base goes where. So if you look at what the simulation actually does, so that's in this plot, you see that initially the system is pushed back and forward very quickly because we're updating the weights quickly, so the system is being forced around. And in the later regime, you get to actually diffusive motion if you get to small update size. So let's see with larger transition times. And then you get the free energy out, which is this black line, and the red is the convolved free energy with the umbrellas. So this shows that it works on quite complex systems. And this is, you need to sample more than this 50 nanoseconds here. So there's a few transitions, you can get some free energy, but the error is going to be relatively large. Okay, so but then what the point I actually wanted to make here is that we have our real distribution, we apply a bias, and we could, for instance, go to a flat target distribution. But the question is, should we actually sample a flat distribution? And that's just a choice we make, and that's a common choice. But I'll show you that it actually, the concept of flat is actually problematic by itself. So for instance, imagine you want to bias along a distance reaction coordinate. Then I can say, I use the distance as my reaction coordinate. Yeah, so that's the square root of dx dy dz squared. But I could also say I use the distance squared as my reaction coordinate. Equally valid, it's the same reaction coordinate, it's just a nonlinear transformation. But is a nonlinear transformation. If I sample flat in a distance, my distance squared distribution will not be flat, and the other way around. So flatness is not a conserved property on the nonlinear transformations of your reaction coordinates. So it's difficult to speak about flat per se. So what this means is that you need a metric to describe distances in your system. So what should you use for a metric? So we came up with this metric that's actually from a collaborator in our department, Jan Klitmar, who had inspiration from this metric from Sivak and Crookes here. So what we're going to use as a metric is a friction tensor. So I look at, so this original metric divided by, proposed by Sivak and Crookes works for a fixed lambda value. So I have fixed lambda. Then I can measure fluctuations in the force and compute the autocorrelation and integrate that. So that tells me how quickly do my force correlations decay. You can actually see that if you would do constrained pulling or umbrella pulling, this would actually be your error divided by the total time length. We now have extended this to work for variable lambda, which has some complications which I don't have time to go into here. But this gives you a proper thermodynamic metric now, which involves dynamics, actually. So the idea is now that since we have a metric into space, we can generate a uniform distribution with this metric. So that means that I set my target distribution as lambda as a square root of the determinant of this metric. So that's standard way of doing flat sampling here. So then the question is, does this actually work? So here's a very simple example. So here, just for testing, so here I look at the potential mean force between lithium and acetate in water. So I chose a very short region here. So here's the contact minimum of the two ions, and here's the solvent separator minimum, which is that state there. Whereas the water molecule, there's a barrier in between because there's one water molecule just doesn't fit in, or it's not so happy here. So then the reference run I did here with a constraint PMF, so I constrain this distance and compute the force. Well, I can also do this with a tighter umbrella, that would be basically the same kind of thing. So then I can compute this metric, which in the constraint case or the umbrella case would basically give you your error as a function of lambda here. So notice that this is on log scale here. So these errors the difference in error are very large. So here it's very easy to sample this in the minimum as well, but here in this middle point there's an issue because the water molecule and the hydrogen bonding network needs to switch between being a water molecule in between and not there. So this actually tells you something. The metric tells you that there's difficulties in the system here, so it's actually a useful indicator of what's problems in the system. But then if you look what happens if you use the AWH method, then the metric drops significantly. So notice this is a log scale, so this is about a factor, what is it, a factor 4 or so? 3-4. So because you let your system free, the friction is much lower. So that's a nice advantage. And then you can see what kind of errors you get if you look at the convergence here. So this is if I would fully optimize my constraint or umbrella sampling run such that I have more points here or longer runs here and shorter here, I would get this red curve. Now if I do AWH, I get this green curve, which is a factor of, 2 or 3 improvement, which is roughly the same as the metric improvement. And then I can optimize, so this was flat, as to say, in the direction coordinate, but now I can do flat according to the metric, which is the blue curve, and I get another improvement of about a factor 1.5. So this shows we actually get better sampling here. Now for a more challenging case, so this is again the DNA base pair flipping, so now I do it not in 1D but 2D, so the orange here is the original reaction coordinate, and then we have a misformed hydrogen bond here in a halfway open state. And we bias that as well, because this is a state which is stuck and is not biased very efficiently with the original reaction coordinates. So now we're doing it 2D to show that it's actually a proper metric in 2D. So we get a landscape with here the original reaction coordinate, here the extra one, we have 2 minima and a barrier in between. But this is the free energy landscape, so this just shows you what the free energy is. But if you look at the metric, it looks very different. So the metric has extreme high barrier here, which is somewhere on this edge of just before the saddle point, which is very high and very structured. So this by itself already gives you nice information of where the problems with sampling are in your system. So then again, I can do the same thing. So this is AWH, the unoptimized is the green curve, and the optimized is the blue curve. So I gain a factor 1.5 here. It's not so much, but it's free. I mean, computing this metric is not expensive. So, and you see that in the end they converge to this 1 over variance goes with 1 over time, as you would expect. Yeah. So conclusions here. So AWH is a robust enhanced sampling method without sensitive parameters. So I think that's actually one of the major, apart from that you want a correct method, it's very nice that there are no sensitive parameters in here. So you don't need to tweak around parameters, you don't need to think like how tight should my umbrella be, how many umbrellas should I have. And the initial update size, you can just have it as large as you want, and unless the system explodes, you're fine. It will it will decrease and things will work. So that's very nice. But a very large PS here, as I also discussed yesterday, the choice of reaction coordinates is still critical and hard. I mean, this method we think takes care of the sampling for you, but if your reaction coordinate is bad, you're still going to have issues, and that's the difficulty in all these cases. So in all applications we have, the major issue is coming up with good reaction coordinates. Now what helps a bit here is that one actually can look at this metric and see like, oh, there are issues here, and then you can look back in your system and see like, maybe there's an issue there and maybe I can improve my reaction coordinate. But the metric doesn't say how to do this. So this method should hopefully be released with GROMACS 2017 if it goes through code review. I can't decide that myself anymore. And so then I think the more interesting part is this metric. So for bias sampling you need a metric. I hope you convinced you of that. And then this friction metric we think is a suitable and meaningful metric to use here. And sampling according to this metric improves your sampling. And it can be used to identify problematic regions. So this optimization we will not have in GROMACS 2017, but this metric will be shown, and this has actually been very useful in many projects to look at where you get peaks in the metric, and then one can look back at the system to see what kind of issues you have there. Okay, that's all. Thank you for your attention.